Today on Hobby Paranormal, this is part 2 of the DIY electric field detector series. In this video, we look deeper into the electric field from a ghost hunting perspective. I'm standing here in my Haunted Mansion set to help create some context to illustrate some of the principles of electric charge and displacement, and question the mental model that we have for how our instruments work. You'll see what I mean by that in a minute. And by the way, this set was made for my second channel, Hobby Halloween. So if you're also into Halloween, then you should definitely check out the other channel. I'll provide a link in the show notes below. Most paranormal investigators rely on standard EMF meters, like this K2 that I'm holding in my hand. These meters are designed to detect electromagnetic frequency, usually the magnetic component, within a very short range. And you'll see that these are more suited for measuring stray AC power fields and don't filter out all that man-made noise. But as you've seen demonstrated in part 1, they have a blind spot. They are deaf to the static electric fields that fill the room. If you haven't seen part 1 of this video series, I will put a link in the show notes below. Here I'll make an analogy. It's not going to be perfect, but in this analogy, think of this room not as empty space, but as a tank full of water. The water represents the invisible electric field filling the space. The water is pushing against the walls of the tank, just like the electric field is pushing against the walls of the room. Now let's imagine that we have a ghost entering the room. Let's assume that it is made up of energy. I'll represent this with a couple of rocks, and I'll set it inside the tank. The water level rises up in the entire room due to a displacement of the energy. Even though the ghost is in the corner of the room, this shows that there's an influence of the field at a distance. Electric displacement isn't the same thing as water displacement. The principle demonstrated here is called Archimedes' principle. Yes, that's the guy from history that famously said "Eureka" while sitting in his bathtub. Recall from part 1 of this video series that we can have positive and negative charges, so the electric field in a room can go up or down. And Archimedes' principle depends upon the volume of water. This small tank is easily displaced by a small weight, but if the same weight were sat in a bathtub or swimming pool, the displacement wouldn't be noticeable at all, whereas the detectable electric field displacement depends only on the distance from the source. But as far as analogies go, it is a helpful way to visualize the concept of displacement. Let's imagine that there's a spirit present in the room with me right now. At what distance do you think the ghosts, or spirits, must be to be detected by different types of equipment? Do they need to be simply in the same room? Or how about a few feet away from the device? Maybe just a couple of inches away, or actually making direct contact with it? This may be surprising, but the answer to that question is not difficult to determine. Depending upon the type of sensor or sensors of the instrument, proximity does matter. For example, REM pods have a very short range of a radius of about 6 inches. And some of the EMF detectors only detect a few feet away, depending upon the type of EMF it is. It turns out that magnetic energy drops off faster than the electric field. Sensors are built to detect specific energy types and will trigger lights or sounds when a set threshold is met. They only respond to the energy their circuits are designed for. Let's get back to my imaginary spirit in the room. This entity may choose just to watch me at a distance and not interact with me, and would easily evade my equipment, especially if it only had a short range. However, as we're discovering in this video series, electric fields are fundamentally different than EMF or the REM pods. Electric field displacement can be detected in the room at a greater distance, so we might have a chance to detect the ghost in the room. But as you'll see, there are challenges with having a sensor sensitive enough to detect it at a distance. The largest challenge for making sensitive paranormal instruments by far is electrical interference. If you've ever heard this sound before, on videos or at live events with sound systems, this is the nemesis, 60 Hz AC power. In some countries they have 50 Hz AC power instead. It's the same issue, just a different frequency. There's no escaping this man-made electrical noise. It emanates from the walls. All the electrical appliances and equipment plugged into this power emit it, and it could even amplify it. We are constantly bathed in it. Our bodies act like antennas, picking up all of the electrical energy in the room. To demonstrate what a massive problem this is, if I touch this scope probe with my finger, you'll see the 60 Hz AC waveform visualized on the oscilloscope. This is what electrical noise looks like to the sensors, and it can be the primary cause of false alarms, especially with EMF detectors like the K2 and Trifield. These meters are designed to be responsive to EMF caused by power mains to identify electric pollution and help mitigate EMF in the environment. They were not designed to be paranormal devices. In fact, if you go into a room and the meter is reading a high level of EMF, it is too swamped to give any meaningful reading. It's essentially useless. However, there is one notable exception, a specialty version of the Trifield modified to filter out AC noise called the Natural EM meter. These models are sought out by paranormal investigators for this reason. These meters have a blue sticker on the face of the meter to differentiate it from the standard model. And that segues perfectly into the next subject. How do we filter out the AC power noise? The objective is to design a filter that blocks 60 Hz while letting all other frequencies through. In this graph, the signal level stays the same from 0 to 100 Hz. You can use your imagination if this graph extends far beyond 100 Hz, but our main concern is what occurs at 60 Hz. The blue line on the graph is at the same level all the way across, meaning that all frequencies are allowed through. This is what an unfiltered signal looks like. To remove the signal at 60 Hz, we must use what's commonly referred to as a notch filter. It would look something like this. You can see why it's called a notch filter. The shape of the frequency response curve resembles that of a notch. I said it looks something like this because in the diagram, the notch is a cartoon drawing of the ideal situation. We'd like for our notch filter to act like a brick wall and reject 60 Hz. But when the filter is built with real electronic components, the actual graph looks more like a curved dip with rounded shoulders. The signal rolls off as the frequencies approach the notch, and inside the notch area, a very tiny signal still gets through, but it is below our threshold that we can essentially ignore it. One of the simplest notch filter designs is the classic twin T. This is a schematic for a twin T filter to notch 60 Hz. It is named twin T because there are two T branches of the signal path that are combining two filters into one. The top components making up the first T form the low-pass filter and allows all frequencies below 60 Hz to pass. The bottom components making up the other T form the high-pass filter that allows all frequencies above 60 Hz to pass. And combined, what's in the middle is the 60 Hz notch. I've constructed a twin T 60 Hz notch filter on a small protoboard. It has 3 connections: signal in, filter out, and ground. In a minute you will see the circuit working, but first a quick orientation on how this lab equipment works. We'll only need 2 pieces of equipment to perform this experiment: an oscilloscope to display the waveforms and a frequency generator to produce them. The frequency is controlled by this knob. I can use it to set the frequency I want. The front display shows the frequency being produced, and the B and C connector is where the signal comes out. This will be our test signal. I will take the output of the frequency generator and plug it into channel 1 of the oscilloscope, and we can see the waveform as the yellow trace on the screen. I'm using a T connector to split the signal to feed it to a small speaker so we can hear what it sounds like as well. I have the frequency at 10 Hz. That's 10 pulses every second. It sounds like a motorboat. I'll crank up the frequency a little bit and stop here at 60 Hz. As I turn the knob, the frequencies on this display go higher, and the scope shows the waveforms scrunching together, meaning that the waves are happening a lot faster in time. Also notice the pitches sound like music notes going up a scale. I'll sweep the knob up and down so you know what that sounds like and looks like on the scope. Okay, that's what this equipment does. Now we're ready to perform our notch filter experiment. For this part of the video, a diagram would be easier to follow. This is the current setup of the lab equipment. To connect the twin T filter into the experiment, I will disconnect the speaker from channel 1 and connect that to the input of the filter. This connects the frequency generator to both the input of the filter and the scope. For this next part, I need a second scope channel. I'll use another T connector and connect it to channel 2. Now the output of the filter can be connected to channel 2. The speaker can also be connected to this as well, and we'll be able to hear the output of the filter. And finally, I'll turn on channel 2 of the scope. You'll see both traces on the screen. The yellow trace is the frequency generator and input to the filter, and the blue trace is the filter output. The equipment is all set up and it's ready for us to conduct the experiment. I'll turn the speaker back on. This is what the output from the filter sounds like. I've put a notch filter diagram in the upper left of the screen so you can see the region of the filter we are in during the sweep. Notice what happens as we get near 60 Hz. The volume gets quieter and the blue trace monitoring the filter is flat. I will sweep the frequencies up and down. The best way to describe this filter is that the sound gets pinched off at 60 Hz. I need to address an issue with the speaker. There's a 60 Hz hum when supposedly we're blocking it with the filter. The AC power fields are finding their way into the speaker being picked up by the cable plugged into it. But if this were a shielded metal box and properly grounded, it would be quiet. Despite the speaker's 60 Hz hum, the blue trace on the scope shows nearly a flat line, evidence that the filter effectively blocks 60 Hz signals. I would be interested to know if anyone uses electric field detectors in their investigations. If so, what type is it, and have you had any success with it? Let me know down in the comments section. We've covered a lot of material in this episode. We talked about energy displacement in a room using a water analogy. We saw the limitations of EMF meters, the huge challenge of power mains causing interference, and a way to filter them out. In the next episode, I'll bring you further updates of my research, and you don't want to miss out on the next video in this series. So be sure to subscribe to this channel. It's totally free. It helps me grow this channel and helps others find this content as well. Speaking of helping out, if you're able and interested in supporting the work I'm doing, I just started a Patreon account that acts as a digital tip jar. But the funds will aid my research and be greatly appreciated. All links, including the Patreon account, can be found in the show notes below. See you in the next video. Thanks for watching.